Okay, so uh, for today's class, actually, we can continue. Uh, we can continue because we already discussed about functions. We can continue from there, and maybe before that, maybe just a reminder that because most of you are still outside of Taiwan. So until November, we will still maybe November. Uh, okay, November. Okay, if not November 2nd or November 9th, we will have the physical class. Okay. So please wait for my announcement, and also for anyone who are still outside of Taiwan during the physical class, that's still okay. I will just keep the Google Meet link open so you can still join the class. So even though it's physical class, usually I'm still using the Google Meet link for recording the session. So uh, the recording session still be there, and I will upload after the class end. Okay, um, let's start. Uh, First, let me review a little bit. Um, so these equations are given. Okay, so uh, to determine whether the lines, we have two lines, right? If we want to make parallel lines, perpendicular, we need to make uh, the gradient to be something. Okay, so for parallel, the two gradients should be the same. Okay? And for perpendicular, you can say that you can write this, or you can write okay. All right. Uh, okay, because we are only around, we should have around 10. And I think most of you are already applied. But before we start this, let me just get straight to you. Okay. Please apply GApps account. Blessing and Andres, you still don't use your GApps account. I know that because you need my permission to go to this Google Meet link, right? So please apply the GApps account. Okay. And uh, the GApps account will be used for the Google Classroom. And I think Blessing and Andres, you still not joining the Google Classroom, and you didn't even know about the homework, right? I sent the homework last time. Okay, so if you still not doing your homework on the Google Classroom, I will not giving you any points. So please apply the GF account. And if you still confused how to apply, please ask your friend. Okay, please ask your friend. And I think it's not about the connections. I think Blessing, you already connecting to Google Meet, right? So you should have connections, internet connection.
Uh, I'm
So
using VPN,
you
sir.
can try to apply the GF account.
Okay.
Okay, so please try to apply this. Because I heard from you from your friend that you have an internet connection problem, but you can join the Google Meet, so it's not a problem, right? So try whenever you have the internet connection, try to apply first. Okay, and I also will give you some probably quizzes through Google Classroom. So if you don't join the Google Classroom, you will not go for quiz, homework, will miss that out. Okay. So do you understand that? Okay. If you still miss out the next assignments, uh, I, I will not grading any one of you. Okay, let's just move on. Okay, we have this requirement here about the gradient for parallel and perpendicular. So if you look here, these two equations, we can simplify both, okay, both of them. We can simplify to become this, and we can simplify to become this, in which we can also observe the first gradient and the second gradient is actually, if we multiply both, we can have -1, which is, we can write that this is perpendicular. And still, the 3 of you get correct. Okay, okay, next. Uh, Asking about the domain. Okay, so for this case here, what should we write about the domain? First, we write, look at the denominator, okay, 3 minus x, okay. We don't want to have this denominator to be 0. So 3 minus x, 3 minus x is not equal 0, or we can write x is not equal 3. That's the first one. The second one is 2 plus x in the square root, okay. The square root need to be at least greater or equal 0, okay. So we need to write this so that we can have this, okay. To make sure that you are correct, please use line number. I've seen your homework and some of you are making some mistakes. So my suggestions is always using the line number to prevent the mistake. Okay? If you have already have a confidence in your answer, and then your equation is correct, you don't really need to write a line number. But if you still think that you need to make some confirmation, some clarification, you need to write the line number. So make the line number and write down all the things that are making the restrictions. Okay. So x not equal 3, x should be greater equal -2. So from -2 here, write this, and 3. And then we need to make that all this to become so we need to make sure that all the points that we are going to observe is we can find in the functions. Okay. For example, if you let the x to be less than -2, maybe -4, -5. If you look here, it will be negative here, which is not correct. Okay, so that's why we can have only this part and this part. Okay? The idea is just trying some numbers that easy to be put in the functions. Okay, and that's why this one here is b. Okay? And I'm not sure whether you are understand or not, but this is not good representations. Okay, to okay? Because all the domain range problem you will still have on calculus. So you need to uh, to understand the problem at the basic of math. If not, then it will be very hard for you to move forward. To move forward. Okay. So I hope you understand this. Okay. And from the homework, I hope you also understand. I think I've checked everything from your homework, but I haven't sent the final score. But I think I will send by today, and maybe I will review your homework tomorrow, so you will have more understanding what you went through the exercise. Okay. 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 Now the chapter for today will be focusing on transformation of functions and also other related things about compositions and the inverse. So first, let me start with the transformation of functions. So if you have any random functions, let's say you have this function here. Let's say this is, let's say, x squared. We can make this x squared to be transformed. We can make it bigger, smaller. Like when you are using, if you are familiar with any design software, usually you can select the picture, you can make it bigger, you can make it smaller, right? So it's actually similar to that features in design software. So if you have these functions, you can make it smaller, bigger. You can move the functions, move to the left, move to the right, right? And then you can also move going upward and then downwards. Okay, so you can transform the picture. Right? So basically, your functions here, you can also transform the functions. Okay, so first we are going to have a vertical shift. Okay, it's called the vertical shift. So we will move upwards and downwards. Okay, look here, from the function f of x, we are moving about c unit. Okay, so what we need to write, we can write y equal functions plus c. That is the transform functions after we move upwards c unit. Okay, and we want to move downwards, we can move from this f of x, we can write f of x minus c. So this means we are going to, so this is upward c unit. Okay. This is downward c unit. Okay. I don't think this is complicated, but I hope you get the idea. Okay, for example, from the functions f of x, x squared, I want to make function of g and function of h. Okay. So what transformations you have in mind is, if I have this function here, all these three functions, and you can draw easily this one, right? You can draw easily and draw easily, right? So let's start to draw the original x squared. Let's imagine this is the x squared. Yeah, just imagine this is the x squared. Okay, now to draw the g and h, we just need to move the functions. Okay, so next time when you maybe read some questions in calculus or maybe in other mathematical problems, you can see like probably you have a functions, blah blah blah, and then you can have the original one without any additional constant. Then you can think from how the function is transformed, and I think it will be easier. It will be easier rather than you are looking at probably here, and you are trying to find 1.1.1 point. And this will be waste of time. So instead of doing that, you can thinking from here and then move the functions. So first for G, we can move the functions going upwards. 1, 2, 3, and we will have here the vertex or the extreme point will be moving 3 units upwards, and then and you don't really need to draw it perfectly as long as you understand the concept and how the graph is originated from. Okay, and then you can also draw the h. It's going downwards, so this will be h and this will be g. Okay, I hope that's clear for the vertical shift. Okay. Okay. Now the other one. Okay. Aside from the vertical shift, we have horizontal shift. Okay. So horizontal shift. So we can move the functions going to the left side or to the right side. Okay. So let me read this to you. To graph this x minus c here. So x minus c is f x minus c. Okay. So we need to move that the functions to the right. Okay. And for plus, you need to move the functions to the left. Okay. So if you have this, if you want to move to the right, c unit, then you must make f of x minus c. Okay. If you want to move to the left, you need to make x plus c. Okay. It's a little bit different from the vertical shift, but it's actually logically true. You're thinking from the perspective. Okay. The previous one is the function itself plus and minus. But here on horizontal shift, we plus and minus the x inside the functions. Okay, I hope that's clear to you. So if we have still we have the x squared and how to make the movement. This is going to the left for a unit. This is going to the right 2 unit. Okay, so instead of expanding the functions and making it like a quadratic function like this, and then probably you need to find where the functions going to have an extreme point and etc. Rather than that, you can just make functions standard x squared. So this is the x squared, and then making another one going to the left. 4 units. So 1, 2, 3, 4. So 4 is here, so it should be around there. And for H is going to have 1, 2. So it's around here. Okay. All right. And again, it doesn't need to be really perfect, okay, as long as you understand how the graph is originated. Okay. Okay. So that's the horizontal shift. So vertical shift, horizontal shift. Okay. Now, how about we can have this how to sketch the functions based on the transformation of functions, vertical shift and horizontal shift. So we have square root of x minus 3 plus 4. So we can start um, from here. Okay, and then we can move the, and make it uh, or let me make a name for it. Let's say we have G, and then this is H, and then this is K. So first we can make the square root of x. Okay, we can make square root of x. And I hope you remember how to draw square root of x. It's actually similar to x squared, but you are rotating the uh, functions, and it's cut into half, okay, because the square root of x, we only have this the positive signs on it. Okay, maybe that is our square root of x, or maybe this is the gx. And we can also make the uh, 1, 2, 3. So maybe 3 here. But this will be the 8x. Okay. And then we are moving 1, 2, 3, 4. So maybe here. This is 4, this is 3. So maybe this is our functions here. Or maybe this is just f, right? Okay. And that's how you make a transformation from the functions that are familiar to you, that you already know how to draw. Okay. Okay. Let's move forward. Now, um, vertical shift, horizontal shift, and then we have reflecting the graphs. Okay. So if you look the picture first, okay, the picture here, we are reflecting the functions mirrored through the x-axis. Okay, through the x-axis. So this is the original function here, and going to be mirrored and reflecting through the x-axis, and the part that are appearing here, that is the negative of the functions, which is the reflection of the original functions. Okay, and if we mirror through the y-axis from this y equal f of x, then that will be uh, f of the negative x. That's the difference. Okay? So if you want to uh, to mirror through the x-axis, you need to make the negative of the function itself. If you want to mirror through the y-axis, you need to have the negative of x, okay, not f of x. Okay, and I think uh, that's quite logical. If you are looking at from here, this is the point, right? And basically, what you are going is you need to reflect this point here and make it here. Right? Basically, you are changing the y. Right? That's why this y need to be equal the negative of the function itself. Okay? Similarly, if you have this, you are actually mirroring this side, right? You are mirroring the x, going to be mirrored through the y-axis, which is you are going to change the x. That's why the negative is on the x. Okay, I hope that you get the logical reasoning. Okay, let's look at what we have here. This is a negative x squared, and then we have another function, square root of negative x. So what will happen if we are going to reflect? Or how to draw this from reflections? So from the beginning, let me maybe. So from the beginning, we know that we have the uh, functions x squared. Okay. Let me just draw the x squared. And negative x squared, meaning we just reflecting through the x-axis, and this will be the results. Okay. So this is the negative x squared. This will be the let's say this is I think this right. And this one here, the original function will be maybe here. This is the square root of x, and this will be the square root of negative x. We are mirroring through the y-axis because the negative is inside the functions. It's only the x that is negative. Will be different case if you have negative square root of x. If this happen, then this will be your answer here. Okay, hope you get the idea. Okay, any questions? Questions? No. Let's move on. This one or the previous one? Uh, which page you want to see? This one or the previous one? Okay. 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 The next thing is uh, stretching and shrinking. Okay, now we have stretching and shrinking, the other transformations. So we can think of a constant. Here we are making a constant c, okay? And for stretching, vertical stretching, if c is a positive value and greater than 1, we say that we are vertically stretching by a factor of c. So if we have first case here, we have this. For example, you have x squared, and then you have 3x squared. It will be vertically stretching. Okay? Let me draw this. Okay? This one here to imagine how the, the function can be transformed. Okay, imagine this is the x squared. Okay, so let me write this is the f of x. And then to stretch this function here, okay, imagine you are stretching the function vertically. So, or even you can try some simple number. For example, if you have 1, it becomes 3, right? But still 0 is 0. So 0, 0 is still on this point here. So 0, 0 is still there. But if you have 1, usually 1 going to be 1, 1, but it's now 1, 3. So it's going to have more points on here. So maybe it's going to be probably like that. Oh, sorry, it should be here. And this will be our g of x, okay? More or less, okay? You can see the proportions on how the functions will go. Okay? Uh, if some question asking you to sketch the drawing, as long as you draw logically correct, not really need to be perfect, but as long as it is logically correct and you are maybe mentioning some important points that are evaluated, it's still correct. It's still correct. You don't need to be perfectly smooth. Okay. And so that will be the gx. And if you want to shrink the graph, okay, shrink the graph vertically, we can write the c here need to be in between of 0 and 1. So maybe a half, or okay, right? And the example here, we have 1 over 3, a third of x squared. So usually we have 1, 1. Now we have 1 and 1 over 3. So maybe 1 over 3 is around here. So this will be maybe around here. Yeah, maybe around here. Let me draw. Yeah, probably there. Maybe it's not proportionally good visuals, but I hope you can see that it make the original functions make a little bit flat, like like from the f stretching to be g, and flatten for h. or it's like a shrinking, yeah, shrinking. Okay. To check the point, you can check maybe 2 until 3 points to check, to imagine maybe in your mind. If you can draw in your mind, you can check. If not, then you can draw the simple drawing, how the function will be when we are multiplying with a factor. Okay. For example, we multiply with a constant, and the constant can be, for example, here, multiplied by 3, this is multiplied by 1 over 3. Or you can also think, if the multiplying by a constant make you not really get the point, maybe you can also think from this. Okay? As long as c is greater than 0. It's actually a pretty similar meaning with the definition here. Okay? If you are confused on because it's only showing you the constant multiplied by the function, and constant can be fractions, or it can be a positive value greater than 1. Okay, that's the vertical stretching and shrinking. Okay, next is, oh, this is example. Now I have 1 minus 2 and x minus 3 squared. Which page, Jordan? This one? Okay. Actually, the notes that I'm taking here, I will be sharing the notes if we finish the functions. Okay. Okay, what function we need to write based on the function of f here? Okay. If we look at the whole function here, there are uh, some parts that we can make a conclusions from here. For example, x minus 3 squared. We can think from previous transformation that it is, we can write x squared, and then we can make it to x minus 3 squared when you move to the right side, 3 units. Okay, so let's start maybe writing the let's say that is our x squared, and then we are moving this x to the right. Let's say that is our x. Okay, let's say that is our x minus 3 squared. Okay, let's say that is our shifting to the right 3 units. And then after we move we need to make uh, twice of it, and we need to make minus, which means we need to reflect the graph, right? So we need to make a smaller version of the function because we need to multiply by 2, and then we need to make reflections. So it should be around, let me make the color. Maybe that is our uh, minus 2. That's minus 3 squared. Okay, so we reflect and then we multiply by 2. Or you can multiply by 2 first and then reflect. So you can check the multiply by 2. Maybe I draw here, this is multiplied by 2. Okay, and it reflect and it becomes this blue one here. But uh, the answer should be have 1. Right? You need to plus 1. So you have this and then you need to plus 1. So we need to move the graph vertically upwards 1 unit. So we need to move 1 unit here. So this will be our extreme point, and we can draw. And that will be our graph. Okay. I hope you get the idea behind all these transformations. So it's vertically, uh, so we make horizontal shift, we make reflection and stretching, and then we move vertically upwards. So this is the first step, and then you want to make it clearly. So this is the second. You make it stretching multiplied by a constant, and then you make uh, third step reflecting through the x-axis, and then move forward and make it to this yellow curve as our final sketching. Okay, now next one. I hope you understand this point here for sketching. Okay, the next thing, aside from the vertical shrinking and stretching, we have horizontal shrinking and stretching. And for horizontal, we need to multiply the x, not f of x. Okay, so to make horizontal transformations, stretching and shrinking, we need to multiply a constant with the x. Okay. So for example, if we start from here, we start from these original functions f of x. We multiply a constant inside the function here. So we multiply with c. What will happen? It uh, will be shrinking. So it's like you push from both sides. Okay. And similarly, if you had this original function f, and then you multiply with c, the x with c, then you have a stretching. The difference between this, the left side and the right side, this is if you have a constant is greater than 1. So maybe f 3x. Okay. Or here, we need to be f, maybe, okay. You can check with a simple equations whether this is true or not. Okay? Because imagine that if you have a function and you have the functions can be changed into triple, then the idea is uh, the smaller the x, the y should be the same. So it's actually making this x here getting smaller in gap. If you can imagine with a simple curve that you can put some x and then you change the x to become 2x or 3x or 4x, it will become uh, getting pushed from both sides. Okay? And we say it's shrinking horizontally. It's shrinking horizontally. If you want to stretch, you need to make with constant that are between 0 and 1. Maybe half, 1/3, 1/4, and then etc. Okay. So if you want to make some simple, maybe just x squared, maybe that's okay. And if we look at, if you have f2x, this will be 4x squared, right? We have maybe half x, it will be 1/4 x squared. Yeah, we can try. And let's say we start with this is 0, 0. So all will be the same 0, 0, the asymptote. And let's say we have, let's say this is 1, 1. We want to be clear. And then uh, for the 4x squared, we have actually this will be no different from the vertical one, but you have different perspective. Okay, just different perspective. And I think it's better to have functions from the, oh, maybe you can try by yourself if you want. Try it from sine x and try this one and try this one. Because if we just looking here, and it is just simply we see the function here is from there. We can say this is vertically stretching, but horizontally shrinking. Okay, you get that? Because we can also see this is, we can say this is vertical stretching, but in terms of horizontal, it's horizontal shrinking. Because you can see that it's going from both sides. So actually, shrinking stretching depends on functions. It can happen from both perspectives. So you can see from perspective that this is happening. So for the f, it is vertically stretching, or you can also say horizontally shrinking. So because it's going from here, and it's also going from here. So no matter what your perspective, both are correct. So both are correct. You can say it's vertically stretching. You can also say it's horizontally shrinking. Okay. I think same way with the this 1/4. It should be getting bigger there, and you can say, oh, it's horizontally stretching, right? You can say that it's getting stretched from both sides, but you can also say it is also uh, vertically shrinking, right? Okay, I hope you get the idea. So I want you to, maybe after this lesson, you can try to look at what will happen here. Is it, maybe this is the beginning, and maybe this will happen, it's getting smaller, and then maybe the last one, it's getting bigger. The gap is getting bigger. Okay. Of course, you can also remember uh, the idea from the the wave functions from the physics. We can also think of that as well. Okay, that's horizontal shrinking and stretching. Okay. 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 Let's move forward. Yeah, I think this is I've told in calculus class also. So I hope you still remember this. So even functions and odd functions. So even and odd, you can determine when you are checking the negative x. If if you check the negative x and it's still, you're still getting the original function when you check with the functions, then it will be even function. If you check with the negative and the result is the negative of the original functions, then it will be the odd functions. Okay, just that. That's how we check the function. But sometimes in the functions that can be uh, so if you are probably uh, determine is it even or odd or neither. Sometimes it can be neither. If when you put in the x, like for example, if you check this one, this one is pretty easy. This will be negative of f of x, right? It will be negative x5, negative x, or you can say that this is an odd. This is odd. But when you have, for example, 2x minus x squared, let's start to check the negative x. So now we cannot make any conclusion from here. So we this is neither odd or even. Okay. Yeah, that will be the transformations of functions. Okay. The next part of today's lecture, I want you to go to for transformations, uh, vertical shift, horizontal shift, stretching, shrinking, reflecting, even and odd functions. That's all for the transformation. The next thing is I'm going to explain to you the composition, or maybe combinations to be precise, combination functions. So um, we can combine functions, like for example we have f, we have g, all defined as a functions. We can say that we can make uh, f plus g, f minus g, fg, or f over g, as long as g is not equal to 0. Right? It's called the sum. For the plus, it's called the sum functions. This is the difference. This is the products, and this will be the quotients. Similar terms will be also used in the calculus part when you are going to have functions and then limit and then derivative. We also call some difference product quotients, and then that's already in really basic in mathematics. Okay, and I don't think the explanation are really needed here. Uh, One point here is the domain is become so domain. So let's say it has domain A, it has domain B. The domain for all these things here, there will be intersection okay, intersections there, and then for the quotients, the G should not be equal to 0. And the rest will be similar. So whenever you have this, and then you will be probably asking the question will be asked about the domain. So keep in mind that you need to combine both functions domain. Okay, and I will directly go to the compositions. So example, let me just get to example. We have f of x squared of x. We have g of x, that is x squared plus 1. And we may define a new function called h, where this h is actually a function of f with inside functions g. Okay. Or we can write this as so that we can write the results as so this function here is originated from this, okay? From this two. And of course, you can see that, oh, this is g, and the square root is from the f. So we put g inside the f. Okay? So we have x as our input. We're going to have So this is input, and this is g, and this will become x squared plus 1, right? And if we put x squared plus 1, going to be having f. So we put f, and then we make the last function here as the result, as the output. Okay, here's the process, and I hope you get the idea here. And I think you're already familiar with these compositions. This is just a review. And we can write these compositions in terms of a composite. The term is called a composite. Let me write the composite for you. So given two functions, let's say f and g. The composite function we call f, and then like a circle there. We call this is a composition or composite function FOG, uh, and it is defined by and the domain is, let's say, defined whenever both g and f of gx are defined. Okay. Okay, let's go for some example. Um, so for FOG, this will be gx inside the f, and write this, and write that this is okay. And GOF, this will be f inside g. So g and then f squared. So we can have x squared minus 3. Okay. To make it more practical, let's go for another example. If f of x is square root of x, g of x is okay. First is FOG, second is GOF, and you can also make it function inside the same functions. Okay, Let me give you a few minutes to try and make some practice. And you can also have uh, composition of more than two, let's say three. You can have five, six, depends on the case, but usually two or three for our quiz in basic of math. Okay, let's start with the FOG. Okay, this is F with a G inside. You can write one by one. So we can write this is square root and then square root. Or we can simply say this is square uh, with the fourth power. Square root with the fourth power. Okay. Second one. Second one system. And then the F inside F. And we can also write this as okay. That would be our solutions. So we can also have the three functions like this one. For example, if I include h as the third function, we can write this as g, and then inside g is h. Oh, okay, the other section, this is about uh, recognizing composition of functions. Okay. So what we have done here is basically we are constructing the uh, compositions from the basic functions from the simple functions, two functions, three functions, right? So the next part here to recognize the composition of functions. let's say we have example, we have and question is find F and G where the big F is FOG. So if we look at the formula, we need to have plus 9, right, inside the root. So we need to first add 9, then take the root. So we can have the inside function. We have the gx will be x plus 9, and the f of x will be square root of. And then when we are trying to compose from these two functions, this is the result, which is the same functions as the beginning. So our answer will be g is x plus 9 and f is the fourth root of x. Okay, maybe some other example before we are moving to the next part. Expressing expressing a function of composition. Express in the form of f. Okay, start with let me give you a couple minutes to try. Uh, squared x plus 9. What do you mean, Kenzie? Oh, you mean for this one? Squared x plus 9. You mean square root x plus 9, like that? And this is square root. You mean this? Yeah, I think that's the correct. Still okay. Yeah, you can have more than one answer as long as it is correct and it's Oh, sorry. I think it's not 4, it's 3. I'll give you a few minutes to try. So you can also remember that this is, so you need to think from the inside functions, which is the h, and then move forward to g, and then you can think the last functions. Now you need to think that this is composed of 3 functions. Okay? If it is 2 functions, you just maybe think from here and then these 2 functions, right? But because if it's 3, you need to think there's another function that um, can be made from the whole functions. Here. Okay, let's start with the first one here. Okay, okay, let me start from this square root of x minus 1 here in the inside. Okay. If we have, let's say, this will be g and h, right? Okay, so which one will be the first one to be inside the function? So I think this should be the first one, the square root of x. That should be the h. Okay, so I will write the h should be square root of x, and then gx will be x minus 1. When combine together and make the g and then h, you will have square root of x minus 1. Okay, and then the last one will be f. Yeah, this is the square, and then you put in this, and it will be your f. It's f g h. Okay, and I think the second one is pretty similar idea. You start from, this is the whole functions. Okay? So we can start from this one and this one. Okay, so we can start with 3 plus 3 plus something here. So we can start from 3 plus x and square root of x, and it's pretty similar that this is probably the h and this will be the g. When you combine these two together, it will be 3 plus square root of x. Okay. And then for the f, we can make this is maybe x, and then it has squared. So we can take squared there. So the f, the big F, we can have, so we will have 2 over 3 plus square root of x and then squared. Okay, help you get the idea there. All right. Okay. Any questions? Why is it squared x minus 1 instead of squared x minus 1? You mean this from here, right? Why it is, so you want to make this, right? Okay, we go your way here. Okay, let's see. Uh, you want to make this inside the functions, but how we can make is correct with this one. The question is this. This is the question. If you want to make this, then it is not applicable to this. Right? So we need to make it. We need to find a way that to make this happen. Okay. So basically, what we have done here is we want to find a way to make these functions happen. How did it start? Okay, we need to make it. Uh, it's like a building blocks. We need to find which blocks we need to put in first. Okay. So if you look here, okay, we want to make okay, first is this. We want to make this first. We don't want to make this. We don't want to make this. Do you get my idea? Hello? Because we want to make the square root x and then minus 1, not the whole square root x minus 1. Okay? Unless the question is asking this, that will be different story. Okay? So that's why we start from here and we need to find a way to make this happen. How to make the square root x minus 1. And then we can have this h and g as square root of x and then x minus 1. Do you get my point? Do you get my point, Helen? Still confused. Okay, so you need to be carefully looking at the objective, okay, the questions itself. What is the requirement to get? Okay, so yeah. So probably in the questions there will be some maybe, yeah, you need to be careful when you look at the question. Sometimes it is making you thinking makes you think that you need to make this and then it's actually not, so you need to be careful. Okay, you need to be careful. Okay. I will go back to inverse, okay, and going from more details, and also this is also important to your calculus counterpart. uh, Inverse or one-to-one functions and their inverse. Okay, so to have an inverse, the requirement is to have inverse. The requirement is need to be one-to-one functions. And how to know whether it's one-to-one or not? So we need to define what is one-to-one functions. Okay, a function with domain A is called one-to-one function if no two elements of A have the same image, which means that is if you have these two, for one-to-one, we have precisely x and y in each point. And look at the other one here. Okay, now look at this, the right side. Look at this. It's getting the same value of the the results, right? It has this, it has this. So this is not one to one. This is one to one. So it should be, whenever you have a different point here, the resulting should be different. Should not be the same. It should be different. Okay. Or I think the visual is useful here. If you have this, you have a functions here, f of x. When you are having a line, a horizontal line, so this is horizontal line, and it's crossing more than one, so it has two. So this is f of x1 and this is f of x2, which means this result is the same, is not our definition here, right? So this is not one-to-one. Okay. But there's a way to make this whole function, this random function, to be one-to-one. We can cut the functions and restrict the domain. Like I said in the calculus, we can make, maybe we can cut here. So until some x here, we are looking at the horizontal line, is pretty much only one, right? And from this perspective, we can say this is one-to-one with restricted domains. With restricted domains. So we can make the horizontal line test, and then we can make and we can determine whether the function is one-to-one or not. Okay, so the function will be one-to-one if there's no horizontal line intersect more than once. So it's only one time crossing the functions. Okay. Okay. Let me give you another example. If I have the x cube. If you draw, probably looking like that. And of course, if you have horizontal line test, in every point here, there will be just crossing one, right? Just crossing one for the f of x cube. So this will be one-to-one function on every point, on every point. And then, like I said before, if we have x squared, okay, If we have a horizontal line test, definitely it's crossing more than one. Okay, so we can say that this is actually not one to one. And then we can restrict the domain. So let me write one more time. We can restrict the domain. For example, we restrict the domain from here, maybe through here, all the way the positive side of X. This will be the domain. So we'll have a new curve here, which is one-to-one functions. Now it's one-to-one functions. And make it a one-to-one function. And then from here, we can actually go to the inverse definition, which is we need to let the f should be one-to-one function. Let's say we have domain A and range B. Then the inverse has domain B and range A. So we exchange the domain and range. That's the definition of the inverse. And then we can define this as for any y in B. Okay, that's the definition of the inverse. So back to this x squared. Based on the functions and the domain, we can restrict the domain, and then we can make the inverse. The inverse on some domain will be square root of x. Okay, let's move forward and going to we are going to have more elaboration on the inverse, and let's see how the inverse property will be having in our discussion here. Inverse property. This is a cancellation property. So when we have a functions, we put inside the inverse of it, the results will be just x. Okay, start with the previous one. I said that if I have this, inverse will be this. And when we put in, it will be squared. If we put in 2, um, it should be square root of x. Remember that uh, usually it has positive or negative. It depends on where we are define our domains. We can have the negative one or positive one. Depends. Okay. For example, we define the domain to be from here or from here. Both has different case. Okay. The first one it can be can make it this one. I can make it the other way around. Okay. Okay, let's back to here. So you can use this property, the cancellation property, to check whether it is an inverse or not. You can plug in the functions or the inverse and check whether it is going to have uh, an x as a result. Okay, the next case is how to find an inverse. So generally, first write the terms of y equal f of x. Solve x in terms of y. And then exchange x and y. And then write down the result as okay. Maybe we start from the find inverse. Let's start with the simple one. Let's say just 3x minus 2. So let's start to write y equal 3x minus 2 and then solve x. Okay. Then we can write this, right? Exchange y and x, and this will be our inverse. Okay. Okay, let's do more. Find inverse of this is with power of 5. Okay, power of 5. This is 2. Try for a few minutes. Check whether you understand how to write an inverse. Okay, so we can write y equals 5. Okay. And we can write this is 2y. And we can write 2y plus 3. Okay. And then we can exchange y and x. So it will be y. We can write and inverse, or maybe just this. This is also okay. That's our inverse. Okay. Lastly for today, let me tell you how to find a graph of inverse. Graphing the inverse. So graph of inverse, f inverse, is obtained by reflecting graph of f in the line y equal x. So for example, let me draw the line first. This is line, let's say this is line y equal x, okay? And this will be, let's say this is our function here. And this will be our inverse here. Okay? So that's the last one. Okay, as usual, okay. As usual, you have pen and paper, you can prepare pen and paper. We will have a quick review for a feedback time. So please prepare pen and paper and your smartphone for scanning the QR code. Okay, let me move to feedback time. So I hope you can do the feedback time. So let me just search in the other screen. Okay, you can use the code for the website if you cannot use the QR code. I'm still waiting to push other students. Okay, let's start. You can pick your name. Only 7 students. Oh, okay. Let's start. Okay, you have around 40 seconds. Look at the graph, and you need to pick out which one is which one. Okay. So from statement A, B, C, D, A is which number, B is which number, C is which number. A, 15 seconds. Need to think fast. 3, 2, 1. Okay, time's up. Let's see if you're getting correct answer. Okay, good. All right. Next one. Let's see who are the fastest one. Okay, good. Jonathan? Okay. Right. Question 2. Let's start. Okay, you need to write down the answer, the number. Write down the number. I hope 30 seconds is enough. I hope 30 seconds is enough. Now, this is composition, but based on the graph. So we need to look at the graph, find out which is the number that is going to have the answers. 3, 2, 1. Any answer can be done. All right. Okay. That's okay. So the answer is 5 based on the graph. Okay. So no one answered correctly. So, okay, let's move on. Still the same because no one answered correctly. So question 3. Okay, I think this is easy. You need to find which one is one-to-one functions. Okay, I think I've made some mistake here, but okay. Okay, it should be 8 and 9. Okay, it should be 8 and 9. Okay. All right. Okay, hopefully you can get the idea. Any questions? I think the last question I have mistakenly put some wrong number, so we will not count the last questions. Okay, any questions? If not, then we'll finish for today's class. So if you don't have any question, you can leave the Google meeting link. Yeah, you're welcome. You're welcome. Yeah, you're welcome.